In this video, we're going to go over why phi, or the golden ratio, is the most irrational number. That's a little bit of a hand-wavy term because it's hard to quantify what do you mean by most irrational number, and so I'll give you what do I mean in a mathematical sense. I'm not a huge fan of this argument, although it's pretty compelling, so I'll leave it at that. It's a pretty compelling reason, but I'm open to additional arguments to further strengthen this case. Alright, so to tie this into the previous Fibonacci numbers and golden ratio video, we talked about leaves and that special angle and why plants maybe might prefer this special angle, although I wasn't convinced that they prefer it. I sort of suggested it might just be an outcome. In any case, so why is phi the most irrational number? You can derive phi in many ways, so you could do it from the limit of the Fibonacci series, golden rectangles. In this case, I'll just use the golden segment. So you have a line segment, and we want to split it in such a way such that A to B is the same proportion as A plus B is to the larger segments. In other words, the larger is to the smaller as the super larger is to the large of the entire thing. So that's another way of deriving phi. And if we do that, I'm going to split this fraction into two. So we have A over A and B over A. That's just a 1. And now we notice we have A over B and B over A. And these are reciprocal. So I'm going to call A over B X. And then in terms of this, that's 1 over X. So that's how I got this key equation. Now, before we continue, I want to thank David Rudder. There's a great response on Quora to this question, and I'm basically going to be following his response and breaking it down a little bit for you guys. So huge thanks to him. The reason I've come across this elsewhere, but I like that he juxtaposed phi next to pi, and I think that really helps hammer home this argument. So that's why I want to thank him. Alright, so using this, we can just replace x, which is what we're trying to find, with phi. We can call it whatever we want. That's our golden ratio. And so there's many ways we could get this, so I'll just present one way. So using this basically says phi equals 1 plus 1 over phi, which we're getting from here. And that means for here, we can again replace this equation with itself. This is a pretty important, awesome idea, and I'm going to do a separate video, a few videos down the road. So if you didn't quite follow this just yet, just stay tuned for a few more videos, but I just want to give you guys some idea of where I'm getting this. So for this phi in here, you can substitute this left definition, which is 1 plus 1 over phi. So you just put that in again, and basically keep doing this infinitely into itself. And that's how you get this infinite thing of 1 plus 1 over 1 plus 1. We basically just substituted phi into here, into here, into here, and so you get this. So this is called a continued fraction. So this is the continued fraction representation of phi, or this number. So there's many ways to represent this. That's just one of them. Now, we can do the same thing for pi, which is 3.14 or whatever. So, and you can represent it this way. Now, how did I get these numbers? You can, if you already know pi, there's many ways to get pi. So let's just assume you already know pi. You can get these by just chopping off parts. So for example, there's clearly a 3, so that makes sense. So 3 plus something better get you this. And so the closest thing would be 1/7. And that's actually where that 22 over 7 approximation comes from. So you could basically try to make it fairly simple and then tack on more and more parts to make it a closer and closer approximation. And that's how you would get these numbers. So approximate it, subtract what you've approximated from the actual number, and then you'll see the difference, and that'll get you the next number. So these are these weird continued fraction representations of phi and pi. Now, so again, we're trying to get to this argument. Take a look at these numbers, 1, 1, 1, 1, 1. These are all 1s, but these are different numbers. These are 3, 7, 15, 1, 2, 92, and it continues to other numbers. What's so special about that? This tells us that, so when people say phi is the most irrational number and hence that's why nature chooses it, they're referring to the fact that these are all 1s. Let's see what that means. So if we were to stop just here, we would get 1. If we cut this part off, we would get 1 plus 1 over 1, so that would be 2. If we chop this part off, we would get 1 plus 1 here, so that's 2. So that would be 1 over 2, that's a half. 1 plus a half is 3 over 2. And if you keep going in this way, you will basically get successive ratios of the Fibonacci number. So it'll be 3 over 2, 5 over 3, 8 over 5, and so forth, 13 over 8. So this means that if we chop this off, we're going to get wherever we're at in the Fibonacci series, that ratio. And so this kind of tells us that using only rational numbers, which are integers, and a ratio of them, we can't really do a great job approximating this number unless we're going pretty far down. So why is that? I wasn't very convinced by that statement. So to help convince you guys, take a look at pi. And take a look at this 292. So let's say you got all the way down here and you're like, I don't feel like going any further, we're just going to get rid of that. 292 is a large number, so let's just look at this in isolation. So we have 1 over 292 plus something. Okay, since 292 is already so large, no matter what we add, whether this is like a 10 or a 1 or a 500, doesn't matter too much because this is already a small number. So in essence, if you find a really large number, which this has, then by chopping off the rest, you're not going to be too far off in your approximation. You're going to have, like, if you stop pi here and said, hey, this is my best approximation, you're going to be within like 0.01% or something of the true value. So this is super duper accurate. In contrast, if you went 1, 2, 3, 4, 5, so like to this, let's say fifth one over here, another one down, you would not be as accurate because that's only a 1. So take a look at this. 1 plus 1 over, let's say, 1 versus 10 makes a huge difference. That's a half, and that's 1/11. So 1/2 versus 1/11 is a pretty huge difference. But 1 over 292 plus 1 versus 10 is not a huge difference. 1 over 293 versus 1 over 302, these are both pretty tiny and they're both pretty close to each other. So the point is that other irrational numbers, whether it's the square root of 2, square root of 3, pi, e, all of these numbers, somewhere in their continued fraction representation, they're going to have numbers that are not all ones. And so in that sense, if you find like one of them that's not a 1 and you chop it off there, you can approximate it better with rational numbers, so rational, these nice whole numbers. Whereas for phi, it's harder to do that because they're all super tiny, so it always makes a big deal. Like we can always do a significant amount better by continuing to go a little further. So in that sense, you might argue that this would be a good idea for nature because you could pack a lot of things like such as leaves pretty tightly and not overlap each other, because by doing some whole number of rotations or like whole number of leaves, you're not going to step on your toes and block the sunlight or something. So in that sense, you could say phi would be a better number or some number involving phi than pi, because this can be better approximated with rational numbers. So like I said, if you chop this off here, you already have a pretty good representation of pi, but if you chop this off somewhere here, you don't really have a great, your accuracy is a lot worse here, or your precision rather. All right, I'll leave it at that. I will see you guys in the next video.